on the Lagrangian, right? So what did we do last time? Last time was very messy. We learned many things, but they are not, you don't need to understand everything, right? I told you about this principle of least action. It's okay if you don't know about it. We are not going to test it, right? This is not a physics class. But you need to understand that in our real 3D space, we have coordinates, and now I call it Q, Qi. Q1, Q2, Q3, maybe just like X, Y, Z. But we're going to expand to some abstract space. So that's why we need I. It can be Q1 to Q1000, for example. This is coordinates, but we can generalize the concept. That's why we call it generalized coordinates. In this class, most of the time we try to look at the real space one at the beginning, but you should have it in your mind that they can be the generalized coordinates, which we will see very soon what they are. If you have coordinates, means position, you should also have velocity. And velocity is defined by dqi dt, right? The change of your distance, that is the velocity, right? And we usually use the dot for d something dt, right? So in a system, if you have the coordinates and velocity specified for each of the coordinates, so be careful when we say each of the coordinates, it doesn't only mean x, y, z, it means the x, y, z of each particle. For example, if I have two particles, to know how the system behaves, I need to know the x, y, z for each particle. So I need to know x1, x2, x3, x1, y1, z1, and then x2, y2, z2, right? For particle 1 and particle 2. So I have 6 coordinates, but I can rename them. I just call them q1, q2, q3. Maybe this is the x, y, z for the first particle, and then q4, q6, q4, q5, q6 for the second particle, the x, y, z of the second particle. Is that okay? And similarly, each of these coordinates have a time derivative. That is the velocity of that component. For example, dq4 dt is the dx2 dt, how fast the second particle travels in the x direction. Right? Because I assign x2 as q4. Okay? So why this is important? Because then we say we introduce a concept called Lagrangian. Lagrangian is just an expression, and it depends on 3 sets of independent variables, right? The coordinate, the velocity, and the time, right? So time, of course, it has to be there, but mostly it is like it depends on the coordinates and the velocity. And I'm not going to talk about the action now, because that is how you derive an equation called the Lagrange equation by principle of least action. And just remind you, Lagrangian, again, is a function of q and q dot. Now I make it vector. If you remember, what is the meaning of vector? It's just a group of the velocity, right? So q dash is just equal to q1, q2, q3, all the coordinates that you have there. I just make it a vector. So it's just a collection of the coordinates, similar collection of the velocities. Again, remember velocity are the velocity components, and also for each particles, right? And how to find it is also defined as the kinetic energy minus the potential energy of the system. Okay? You just take it for granted. And then, in order to find the equation of motion of a system, we just need to memorize this Lagrange equation. If you can memorize that, will be great. If not, write in your cheat sheet. But more importantly is that you need to realize that it has a partial derivative with respect to each of the velocity and coordinates pair. So if you have 1 degree of freedom, what's the meaning of 1 degree of freedom? Maybe you have a particle which can only travel in x direction. So to specify the location of the particle, you only need to say it is at x equal to 5. And of course, you also need to say it's a velocity of 5 meters per second. Then you define the whole system, right? So then I is just equal to 1, right? So, but if you have, let's say, 3 degrees of freedom, like what I'm saying here in our 3D space, with one particle, let's say only one particle, then you have 3 equations. One of them is with respect to the x direction, right? This may be, to be specific, this one may be Q1, Y may be Q2, Z may be Q3, right? So the number I run from 1 to 3. And similarly, V1 may be Q1 dot, V2 may be, it is Q2 dot, right? And V3 is Q3 dot. Is this okay? So you understand you have n degrees of freedom of the system, then you have n Lagrange equation. Okay, so we don't go into the background, right? I'm also not good at that, but all we need to do is that we know there's something called Lagrange equation. So how are we going to use it, right? But before we continue, I need to introduce another concept. You have the coordinates, you have velocity. We also introduce something called generalized momentum, which will be used very soon in the Hamiltonian mechanics. So this one, you cannot use our regular definition. The definition is what? Pi equals to the partial derivative of Lagrangian with respect to the velocity, Qi. Okay? Most of the time, yeah, momentum equal to mv equal to mass times q dot. But it is not always the case. So from now on, you should not take that equation for granted. This is the definition of momentum. P equal to partial L partial Qi, right? The easiest thing to do is let's check it, right? Just a very naive checking. Because if this is correct, it should agree with our understanding, right? For example, I have a particle, right, at Q, at position Q, right, with velocity Q dot. Just a particle, 1D particle, for example, at location Q, traveling at Q dot. So what is the kinetic energy of this guy? Based on your Newtonian mechanics, right? Or you learned earlier. What is the kinetic energy of a particle traveling at velocity q dot? Thank you. 1/2 mv squared, right? Equals to, here our v is just q dot. Is that okay? Half mq dot squared. What is the potential energy? Of course, you don't know because I did not give you. So we just say it's a function of Q. Okay, it can be a complicated function, but it's the function of Q, right? And I just recall we also call the kinetic energy equal to T, right, since the last slide. And we also call the potential energy equal to V. So what is the Lagrangian of this system? Definition is, let's go back, right? What is the definition on the top? T minus V, right? So do not ask why, right? We don't have time to ask why. Of course, you can go to the physics textbook to understand more. I don't know well neither, but just take it for granted. T minus V, right? The definition is kinetic energy minus potential energy. So Lagrangian is 1/2 mq dot square minus u of q. This is very important. You tell us that the kinetic energy only depends on the velocity, and the potential energy only depends on the position, right? So now, then you tell me, what is the momentum of this particle? Of course, we know with the Lagrangian, we already know that, right? What's the momentum of a particle moving at velocity v? mv. Let's see if that is the case. Based on the definition, is partial L, partial Q dot, right? This is the definition we just gave you. So you should give me mv. If it is not, then then this definition has some problem, right? So do you know how to do this? We can do it carefully. Equal to partial, the first term is 1 over 2mq dot square, partial q dot. The second term is partial u of q, partial q dot. This is a partial derivative. What is the value of the second term? 0, because you may have a very complicated potential, maybe q to the power 5 times e to the power 6, whatever. But it all depends on q. There's no q dot. They are independent. So do not mess up. Do not think that, hey, but there isn't q dot and q has some relationship because q dot equal to dq dt. But now we treat it as independence variable. You need to look in this way. Right? So I do not have q dot in this equation. So partial u, partial q dot give me 0 because they are not dependent on each other. Then how about the first term? How do you do the differential? I do have q dot, right? First term is partial, this one partial q dot. So q dot square becomes 2q dot, right? So this gives us mq dot. Right? Which is just mv as what we are expecting. Yeah. Magnitude. Here is magnitude. What is other? Because we are taking the magnitude of each component. Right? So here I only have 1 degree of freedom. So you only see this P equal to mv, right? But if I really go full, if I have many degrees of freedom, it's Pi equal to partial L partial Qi. Then I have x, y, z. I have the 3 components of the momentum. Then it becomes a vector. Yeah, very good question, right? So here looks like just a scalar because I'm talking about a 1D case. Okay, so in 1D case, this is a vector already, plus minus q, give me the vector. Yeah. Okay, very good. So this is what, I mean, we did not prove anything, right? But we just showed that now I'm very more comfortable that, yeah, this definition of momentum probably makes sense because it agrees with my learning since middle school or whatever, high school, right? It agrees. So then I will just put this in my cheat sheet. If I can memorize, I memorize. If not a big deal, right? I can always ask ChatGPT, but I should know that. Okay, so then let's see the power, right? How we use it. So now we will start talking about a free particle. Let's consider a 1D case. The question is, a free particle means what? When it is a free particle, it means potential equal to 0. Right? It's just saying that no one is controlling me. I don't feel any force. Then, of course, potential need to be 0 everywhere, right? Maybe in the vacuum, the space, right? So also I make it 1D case. Then what does it mean? What are the coordinates that we have if this is 1D case? We basically just have q1 equal to q, right? I only have 1 coordinate. And then the velocity, I also only have 1, which is q1 dot equals to q dot, right? I just, instead of keeping the subscript 1, I just, to save my time, I just try to remove it. So now I only have q and q dot. So the first thing, in order to use what we just learned, I first need to find the Lagrangian. What is the kinetic energy? Again, we just say that it is equal to half m q dot square. because it's kinetic energy. That's the definition, right? What is the potential energy? 0, because this is a free particle. Okay? So as a result, the Lagrangian is T minus V. I need to go through this step by step, make sure that I'm correct. It becomes 1 over 2 mq dot. Do not skip this step. So very simple, right? This is the Lagrangian. Then what is the equation of motion, right? What is the equation? Then we use the Lagrange equation to find the equation of motion. Basically, I want to know how this particle will behave. I then use the Lagrange equation. And I can copy it, right? It's d dt partial L partial Q dot minus partial L partial Q equal to 0. This is given. And the way I memorize it is like this. Definitely it depends on Q and Q dot, right? So it's partial L partial Q dot. And they should have the same dimension. Q dot is dq dt, right? So dt can get cancelled. Then you get back dq, right? So then have the same dimension. That's how I memorize it. D the whole thing dt and then dl dq dot. Think about that if you want to memorize. So then what do? Then it means the equation of motion of the system is, I'm going to write d dt and partial L. What is partial? What's L? L is 1 over 2 mq dot, right? We just square partial q dot minus the whole thing 1 over 2 mq dot square partial q equal to 0. Right? What did I do? I just substitute L, Lagrangian, half mq dot square into this equation. What is this term? 0. Because this term does not have q. So partial this term, partial q is 0. And this term is just like what we learned earlier, right? We tried earlier. This is just equal to d dt and then mq dot. Right? Because this is just q dot square. So you partial q dot, then you get 2q dot, right? So it becomes nq dot. But you need to further to dt, d the whole thing by dt, right? But if you don't know, remember this is just equals to mq dot dot 0, right? Because if you have one more dt second derivative, you just put one more dot. So this is just the convention. What is the second derivative of position? First derivative is what? Velocity. Second derivative is acceleration. Very good, right? So it means q dot dot, which is just a, equal to 0. This is acceleration. So basically, by using the Lagrangian, it's telling me that if your particle is a free particle, it has no acceleration, which is just the Newton's first law. You will continue to move at the speed that you have. So, but what is the point? The point is that you already see the power. If we know this Lagrange equation, I can use it to derive this Newton's first law, right? So, I mean, just show that it is working. That's it. Any questions? Think about it. Now, if this is okay, let's do a more complicated but example. So you have learned this simple harmonic oscillator, right? A mass attached to a spring with a constant K. And if you forgot, I just remind you that the force, right, equals to negative Kx, right? You stretch it by x. X means the delta, how much you stretch the spring, right? If you have a positive stress, the force is going to pull you back. If you compress the spring, then it's going to push you away, right? That is the force. And you probably remember, for those who have not learned this Lagrangian mechanics, you probably remember it was very difficult to solve this problem. We need to do F equal to ma, right? Come up with all the force. Eventually, you come up a result that it will oscillate a certain frequency. Now, we use the Lagrangian mechanics to try this now, okay? So the first thing, because Lagrangian equals to the kinetic energy minus the, let me just use the term T, potential energy. So I first need to find what is the kinetic energy. Again, the kinetic energy has nothing to do with how I'm attached. It's just equal to half mv squared over q dot squared, right? The kinetic energy, it has at any moment, it's just half mq dot squared. The only thing that is different is the potential energy, and this one we actually need to borrow from what we learned before. What is the potential energy? Do you remember what's the potential energy for a mass attached to a spring with Hooke's constant K? No, that is the force, minus Kx. Yeah, Ks squared, very good. So instead of putting x, I would say kq squared, right? So here I would say x equal to q. Again, this is a one-dimensional system, right? I only allow you to oscillate left and right. Now this one we did not prove it, but you can do integration, right? Force is minus kx, then you just go through the math, then you know this is the potential. But yes, so this is a little bit cheating, right? But same for kinetic energy, right? What is the kinetic energy? Why is half mv squared? We also need to prove by integration. Right? Okay, so is it okay with the kinetic and potential energy? So as a result, is Lagrangian equals to half mq dot square minus half kq square, not plus, okay? It's minus because we're talking about Lagrangian. So I'm going to do step by step because I know what I need later, right? Because I know that for the Lagrange equation, I need to evaluate partial L, partial Q dot, and then dt. Also partial L, partial Q. So I'm going to evaluate these two terms. dt partial L partial Q dot equals to ddt, right? Partial, I will just put the whole thing. For those who are familiar with this, probably can see it right away, but let me put the whole thing. Half m dot q, not m dot q dot. Now my system is very slow again. Square minus 1 over 2 k q square partial t. Are you okay? Partial q dot. Are you okay with what I'm doing here? I just want to evaluate this term. I substitute L. Now I have two terms. What is the first term? Partial half mq dot square partial q dot. Give me what again? What is this term? Partial. Yeah, thank you. Mq dot. So this is mq dot. And that's it. I claim that the second term is 0. Wow, it's not responding. Do you agree? Because the second term only has q, it does not have q dot, right? So the first term actually gives me m, like what we did earlier, q dot dot. M times acceleration, okay? Now I also need another term which is partial L, partial Q, right? So let me go through the same process, partial 1 over m 1 over 2 mq dot square minus 1 over 2 kq square partial q. This time is partial q. So what is the value of the first term? 0, thank you, because the first term only has q dot. Remember, q and q dot, velocity and coordinates, are independent variable in this formalism. The second term is what? Minus kq. Very good. So what is the Lagrange equation? It will be mq dot dot, right? This is the first term, minus kq equals to 0. Are you okay? Because it's minus potential energy, and my potential, no, I mean not minus potential, I mean minus partial L partial Q. Minus, and the partial L partial Q is minus KQ, right? So this gives me Q dot dot plus K over MQ equal to 0. Now, if you recall what you learned before, this is exactly the correct equation for simple harmonic oscillator, right? Because I can further write it as Q dot dot plus omega 0 square Q equals to 0, where omega 0 equal to square root K over M. If you remember this, the resonant frequency is square root K over M, right? The constant. And if you want to see clearly, this is dq dt square plus omega 0 square Q equal to 0, right? This relates, or maybe even better, we just call this X. This one tell me how its position changes as a function of time. And you know the solution to this is, do I have the solution? I don't have the solution. It's just A cosine omega t plus B sine omega t. So that it means it's oscillating, which is correct, right? So you see that I use, and you see that it's very simple. I actually write so many things because we are using it. For those who are familiar with this, you get this right away. You see, it's so easy to come up with the equation of motion with Lagrangian, and that's why this is a very useful tool. And now we are using the real coordinates and velocity, but we can use it in the phase space, which you will try in your assignment, and also when we are doing the simple harmonic, the superconducting qubit. So is this okay? Okay. Now this is not still not useful to us. The reason we want to do this is because now we want to introduce another formalism called Hamiltonian mechanics. With this formalism, we can then do some promotion of operator. Then we